We're going to talk about delivering GraphQL. So we're not just going to talk about GraphQL, but we're going to talk about implementing a GraphQL server. So by the end, we should be able to implement a rudimentary GraphQL server that we can at least get up and running and serving HTTP requests, and then something you can iterate off of. And the code is in GitHub, so I'll make a plug for the repository at the end of the talk. So first, I want to talk about what GraphQL is. So you think about when you have a REST API. So here, I want to get all films. This is GraphQL, but imagine it were REST. I would say I want the list of all films, and it's going to give me their title and their ID. And now if I want detailed information about all of these films, I have to make 1, 2, 3, 4, 5, 6, 7 repeated calls using each one's ID to probably a different endpoint that gives you more details about this record. This is not very convenient for even like a web page, less so for a phone app. You can imagine like data and latency are a big deal on phone apps. So one of the goals of GraphQL is to give application developers a language for specifying their data requirements so that they can get everything they need to create a application view in one request response cycle to the server. So now this is a GraphQL API. So here is the language that I can write my query in. And if I want the detailed information on all of these, I can simply specify exactly what I want instead of making multiple calls. So here I've said I wanted the episode ID, the directors and the producers of each of these films, and I get it. Another thing I can do is I can do nesting. So let's take a look at what else do we have inside films. Let's take a look. So we have all this wonderful documentation that's generated for us. This is pretty great. So I'm calling all films as my top level query. This all films. It gives me, well, it has some arguments. Look at that. It has some arguments. I didn't specify any arguments, but if I wanted to, I could have. After. After is a string. Afternoon. Let's see what that does. Nothing? I don't know what it does. Oh well, whatever it does. Let's say first. 3. Now I get the first 3 films. Or if I want the last 2. This is very important, by the way. We want the first 3 Star Wars films and the last 2 Star Wars films, right? Okay. Oh no, I got it wrong. You know what it is? It's off by 1 error, right? Okay. Yeah. Okay. Well. Oh, actually no, it doesn't. It doesn't have the newest one. That's the problem. So just the last one will be sufficient. There we go. This gives me a films connection. What is a films connection? So we drill into that. Films connection has page info, edges, total count, and int. So I didn't ask for any of that, but if I wanted to, I could page through the films. Say therefore there were thousands of films. I could page through them. Let's get the total count. And we get 7 right here. So maybe I need the total count for my web page, and I can ask for it if it's exposed like this. And then let's see. So then what else? Let's drill into what's edges. Edges looks weird. Edges. Now, oh, look at this. Syntax highlighting. My query turned red. Why did it turn red? Because I need to specify at least some information about the edges that I want to get. GraphQL will not give you any information that you don't specifically specify. We'll talk about why that is in a minute. So let's drill into film edges and see what's in there. Film edge, it has films, nodes, so on and so forth. So we can nest into this. So node has a title, and a node also has an ID. So let's get the node in the title. Okay, I'm not making very good use of this because I'm duplicating information, but in principle, we could have highly structured, very nested data and get all of it in one request response cycle. It's probably a better entry point to demonstrate that. So what other entry points do we have? All people. People sounds good. So let's look at all people. So we want all people, and we want total count. And of the people, we want name, home world, film connection. What's a film connection? Films, title. And now we can see all of the, we need an ID for home world. We can see all of the films that a character is in. Luke Skywalker is in these films, so on and so forth. So we basically have, we got to do a join simply by expressing it in this language. And the application author didn't really have to anticipate that we would want to do that join. They simply expose the film connections as a nested data structure, and the library that we use knows how to look up the information from a film for a films connection, and so it can kind of build this join on the fly. So we don't have to anticipate what users are going to need. This is very important if the front end has to iterate very quickly. They don't know what their data requirements are going to be until later. So we can expose, instead of exposing particular endpoints that give them some rigid set of information, we can expose a language, a declarative language that allows them to specify their data requirements. So this is GraphQL. What we're looking at is a tool delivered by Facebook called GraphQL. And this is for the Star Wars API. So this is a toy demonstration, right, for Star Wars. But just to show that there's a real use for this, here is GitHub. GitHub exposes a GraphQL API that we can use. I'm logged in as myself. You have to log in to use this. So I can see viewer, that's me, and you can see my bio. Oh, I'm a mathematician writing Scala at CJ Affiliate. That's cool. Repositories. Of my, I want the last 5 repositories. Now I want the nodes inside there, name, description, and say commit comments. And drill into that. Get some commits. Well, let's forget about the commits. But anyway, so we'll look at this here, and we can get this information here. Oh, Sangria Argonaut marshalling, Haskell teaching material, minimal paths on a graph. I don't see this one here, but this one is, let's look at the last 10. Sangria demo. Here is the repository for the talk, today's talk. So you can access GitHub for your own data or for other data that you're authorized to see using a GraphQL API. So GraphQL, the same thing, this open source tool, is one of the tooling behind that. One of the nice tooling you get for free when you implement a GraphQL server. So first off, GraphQL is not a tool or a program. GraphQL is a spec. If you implement a GraphQL server, the spec is kind of very rigid, and so you get a lot of tooling like this GraphQL for free. GitHub gets to use Facebook's client here simply because GitHub exposes a GraphQL API. Here's another one, GraphQL Voyager. This is GitHub's API as well. This is a pretty intense API. Hard to get a grasp at everything all at once, but they always start from here, this entry point query. And we can see we can go into, say, user. What does a user have? User has repositories. Okay, repositories have lots of stuff. But you can get you can zoom in and check out different parts of the API and see how they're interconnected. For instance, look at this thing right here. This thing has a bunch of arrows. What is that? This thing is a commit. Well, it makes sense why there are a lot of things pointing to commit. That's the main thing of GitHub. So, so you get this kind of tooling for free when you implement a GraphQL server. But not only that, the way I like to think about GraphQL is REST a la carte. So when you have a REST API, one thing we talked about is nested data and having to make repeated calls to get the information you need. With GraphQL, you can craft your response to get all the information you need. And not only all the information, you can also avoid the information you don't need. So again, part of GraphQL is that it does not give you anything you didn't ask for. So the two biggest problems with REST APIs are underfetching and overfetching. And that's really the problem that GraphQL seeks to solve. So that's our little introduction. Let's get to the topic. Let's see. Okay. So, delivering GraphQL services using Sangria. Let's see. So we're going to go into about four parts. First, designing your GraphQL schema. So the way you design a GraphQL schema is a little bit different from how you would design a REST API. Then we're going to talk about going and implementing your server. So that involves your data layer, and it involves query execution, and it involves defining your schema in Scala code. So we'll take a look at those four parts in total: designing your API, designing your data layer, query execution, and writing your schema in Scala. The great library that we're using is called Sangria. It's open source. It's very idiomatic Scala, and it's really a pleasure to use. We haven't had any trouble with it. So here, first let's start with an example of GraphQL's schema definition language. It looks kind of like, almost a little bit like pseudocode, but this is a language that's part of the GraphQL spec that you can use to define your schema. GraphQL spec defines two languages, the query language and the schema definition language. And so we're going to see a lot of stuff like this. And I want to show you an example because we're going to have to look at it without highlighting. I don't actually have highlighting in my slideshow. My slideshow is not that advanced. But it looks more or less like what you'd expect. You have types with fields. Those fields have types. Notably, exclamation point means non-null, means non-nullable or required. So if you see something without an exclamation point, that tells you that that's either nullable if it's a field or optional if it's an argument. Lists are denoted with square brackets. So this is a non-nullable, so required list of non-null, like real actual posts. So either of those could have been null. You could have an actual list that has 5 nulls in it. That would be horrible. Or, but here we say neither of those are null. These are these ats are annotations, and annotations don't do anything for the schema definition language, but they're used by some preprocessors. So here, let's imagine that we have a very simple app that has a very simple data model. We have a database. This is no language in particular. It's like database pseudocode. But we have two tables, foo and bar. And every foo has a bar. Of course, it doesn't have the full bar because we're good programmers and we normalize our database. So we have two tables here, foo table and the bar table, and a pointer or a foreign key into the bar table for every foo. So we can represent this in GraphQL in kind of a straightforward way, where we have foo as a type, and here we've mimicked exactly what's in the database. And bar is a type, and we've mimicked exactly what's in the database. And we want to expose these to the user, so we have to create an entry point. This capital query object is a reserved name, and it is the entry point of a GraphQL API. So here we have completely mimicked the database structure. But we could do better. Right? This is GraphQL, and we can have nesting, deep nesting. So what's one thing that we can, what's one improvement we can make right off the bat if we allow nesting?
The relation between foo and bar?
Exactly. A foo is related to a bar. Every foo has a related bar, but the database only keeps the bar ID. But that shouldn't stop us. We can actually put the actual bar in here. So we could do that. There's a less obvious improvement we can also make. For every foo, there's a bar. So there's a one-to-one relationship for foos to bars. This means that implicitly there is a a one-to-many relationship between bars and foos, and we can put that in our we can expose that in our API. So now every bar has a list of foos. Maybe that list is empty, or maybe it has a dozen, or maybe it has 1,000. But we can expose it that way. Notice that these are also mutually recursive. Not a problem. Okay? So we don't have to expose our data this way, but if we wanted to, we can. Finally, here we get the list of all foos, or the list of all bars. Maybe that's too much. Maybe we need to restrict that somehow. A great way to restrict a data set is with arguments. So here I've put some basic arguments in here. If these things had date or shirt color or something like that, you could also use those as arguments to restrict the output set. So here, foos and bars, we can say, well, I only want these particular foos, or I only want these particular bars. And this argument is optional. The contents of the list are required, but whether the list itself is there is optional because it doesn't have an exclamation on it. So users can call it if they don't know any IDs off the top of their head. They could call it and get everything if they wanted to. Another popular thing to put in there is a limit argument, like limit 3 or something like that. Things that you'd expect to have in SQL. So here we've taken this normalized database and we've turned it into kind of this denormalized structural representation. So any questions on that part?
So let's see if bar had a color, would you need a separate line in another query type for that? Or can you append it to as another argument to bars?
So if bars had another field,
right.
So say for color, for instance, so if it's in the database color, we could put another one in there. You mean like extend it after the fact, or
I mean when you're making a query and you want to do it by color?
Oh, so yeah. So what we would do is we'd have another field here, and if we wanted to give users the ability to filter by color, we would need to add it as another argument.
Okay.
Right.
How about the type safe, like if I misspell foo, the compiler will check it, or just foo is just information?
So it's funny that you say the compiler, because the thing that's compiling the GraphQL queries and the GraphQL schema definition, so we're not writing this in our Scala code in a certain sense.
Okay.
However, this does get compiled by some tools, right? And so it will check it, and it will check the validity and things like that. And then queries can be validated. And in fact, our library validate can take a query, and not only can it check if the query is syntactically correct, but it can also validate a query against a particular schema. And so ours will do that. So it is type safe in that sense.
Okay.
But the compiler, so to say, is part of this library, and you pass it a schema, you pass it a GraphQL query, and then it checks it. Okay. Anything else? So that's kind of all it is for the simple example to convert it into a GraphQL schema. Next, let's talk about how the library, Sangria, will allow us to execute GraphQL queries. So assuming we've set everything up, let's look at how query execution happens, which is really what you were asking about. So we write our schema as a Scala value. We don't write it in the schema definition language. We have to write it in Sangria's DSL, which basically means we're taking the schema and we're kind of compiling it by hand. I don't know. You'll see what I mean later. But you write out your schema as a Scala value. When you get an incoming request, you create a context. So your context can have basically represents your data layer to the library. You'll notice that it's also encoded in your schema as well. So your schema is parametric over this context type. So you can have a different, to allow you to use whatever type you want from your application to bridge between your application and Sangria. You get the unparsed query from the, you parse that out of the HTTP request. Sangria provides a query parser that will just check the syntax. And then here's the main meat of the query execution. Executor.execute, provided by Sangria, validates your query against the schema, comes up with an execution plan, and uses your context to fulfill all the data and build a JSON. And then it gives you a JSON blob, and you can serve that to your customer. So is this okay?
What's the second parameter on schema of this unit?
This is a little bit weird. So, yeah, I don't think it is supposed to have a type parameter. I think that's kind of a like a relic in the library for backwards compatibility, maybe, or something like that. But really, this one will always have to be specifically the Scala unit type. I think. I could be wrong. But the reason that it's here is because schema extends another class that has 2 parameters where it's not always unit. And so I think that's why it's there. I could be wrong. But we always have a unit here in our schema. Okay. So we've talked about query execution. Basically this small part. That's the part that the library writes for you. Now the library can't write your data layer or your schema for you, so that's the bulk of your application. So here we define our data layer. We look at our database, and we write case classes that correspond to the physical layout of our data. Now GraphQL, another great use for GraphQL is aggregating multiple data sources. So not just a single database, but you could have pull from a database and a REST API, and you can consult the time of day or whatever. You could draw from multiple data sources. And but your case classes here in your data layer should always reflect, I say always, I take it back, but generally reflect the physical layout of the data as you can get it. Okay? So we have, when we look up a row in the database, we're going to have this information. We also have to make a context that we use to parameterize the schema and executor.execute. But what goes in there, we don't know yet. We don't know until we go and write our schema. So we'll have a couple of methods here that the executor will have access to in order to fulfill queries, and we'll find out what those are and fill those in later. Copacetic? Okay. So now implementing your schema. All right. So here we have our data layer. I took bar out of here. We're going to focus on foo for a minute. Bar is still there. I'm just not looking at it. Also, we have our GraphQL schema. And we have to essentially compile this GraphQL code, kind of write the AST here in Scala, in the library's ESL. I've also aliased some of the library objects. So the alias is here. In Sangria, it's not called a GraphQL object. It's called object type of context and whatever. I've aliased it so that it's more obvious when we see something coming from Sangria's library, because it gets very confusing. So anything coming from the Sangria library when we go to run our schema will be prefixed by GQL. So we need to create a Scala GraphQL object corresponding to this GraphQL schema. Fortunately, the library provides some macros that can look at a case class and grab the fields out and do the right thing. What's the problem with that, though?
You can represent like bar, send of bar ID.
Right, exactly. So if we rely on the macro to generate the entire, this entire GraphQL object, it's going to mirror the case class, but we want it to reflect the GraphQL schema. Well, the macros can be given directives, again from the library. And I didn't preface this. This should be like, this comes from the library as well, but it's, I don't know, it's an argument to the macro that says we want to replace the bar ID field with something else. Well, with what? Well, we want to replace a field. We want to replace bar ID with a GraphQL field whose name is bar, whose field type is lowercase bar. Now, right now, that's an undefined symbol, but it's the other GraphQL object, basically the brother of this one, if you will. And so that's why I've made this a lazy val, because the bar will also have to be lazy as well, because we have circular references, so we need to hoist everything. So we hoist everything with lazy vals. So bar you'll see on the next couple slides when we get to it. But the type is bar, which is a GraphQL object. And here is the resolve function. And that's kind of the meat of what goes on here. This is this is the adapter between our schema and the data layer. The resolve is a callback that gets past the executor. So remember executor.execute. The resolve will get past the state of the executor. So imagine this is in the middle of query execution. The executor has accepted the query. It knows the schema. It's fulfilling a query, and it has some information, some meta information, and that's what this executor has. In particular, it has a value called context, which has this type. It has a field called context. It has a field called value, which has this type. So you're going to get past the context and a foo, and then you're going to have to now say how you're going to get a bar from that. So let's see how we do it. And this is where we start filling in our data interface. So we see, okay, we take the information that we have right at that moment. We have a context, and we have a foo. The executor has a context, and the executor has a value, which has type foo. And we say, okay, well, let's just create a context. Let's create a method inside context that will give us a bar. And really will give us an action of context bar. So this context has to match this context, has to match the context in your overall schema, so on and so forth. This bar tells you what's inside there. This kind of the bar is the payload. The context is there kind of just to constrain the type. Now an action is, Sangria provides kind of a whole class hierarchy of action types. So you have action types which are called partial values, future values, partial future values, and so on and so forth. And but an ordinary all by itself bar is a valid action. The reason for that is so that when you're implementing your context, you can control concurrency. You can defer lookup of one thing until you found something else because maybe that's more efficient. You can implement caching. You can do everything asynchronously and concurrently. You basically have all the power of a Scala future and a little bit, I was going to say and a little bit more. Not more, but it's a little bit different. It's kind of similar to a Scala future. So you have some tools you can use there. So that's why we have this action. But you can think of it as just wrapping a bar with maybe some extra instructions. So the pattern we followed is we take our case class, we replace or fill in what we want to change, and when we get to a point where we don't know what to do, we put it in our data layer, essentially. Remember writing our schema and then we're like, okay, we have to do something now. We have to give a bar. We need a new, we can solve that by making a new method in our context. So now let's implement bar. So here's the GraphQL object bar. And it ends up being very similar, except instead of replace fields, we want to give a different directive to the macro. We want to add a field instead. We want to add the foos field. And how do we calculate those foos? Don't worry about it. Just make another context method for it. Basically, worry about it later, move it to the data layer. And these both should be actions. Action of bar, action of foo. It's just an old version of this where I didn't have the actions. So it's a typo there. Okay, so this is bar. Now the last type in our GraphQL schema is the query. Again, query is a reserved word in the schema definition language. So the query is the entry point of the API. And we wanted 2 entry points, foos and bars. And here's where it gets a little harder because these are not really data objects in the sense of the other two. So we don't have a case class to base a macro off of here. So we have to write these by hand. So we'll write a query, but other than that, the query will be a GraphQL object just like the other two. Now here we have these type parameters. Again, context, that's the same. The second one though is unit. Now let's go back. Here we have a context and a bar as the type parameters. And those are the things inside the executor. So we say, okay, if we've made it this far to where we're calculating a bar, we have a context in our hand. The executor already has a context in its hand. And the executor has a case class bar at its disposal to use in order to create a GraphQL bar. So we think we're in the middle of query execution. We've retrieved a bar from the database, or we can if we need to. And we have this context in our hand already. And so both of those things are going to be in the value that gets passed to our continuation. Because we're in the middle of a query. With the entry point, we haven't computed anything yet. So we don't have a bar in front of us or a foo in front of us. But we need some type to put in this right here. So we put unit there. So the things we have access to, we have a context, and that's it. So let's start implementing. These query foos and query bars in our context, those are going to need some arguments, in particular because the entry points themselves have arguments. So let's fill out the type signature a little bit more. So we basically read this, and there's a logical mapping between GraphQL types and Scala types. GraphQL lists kind of map to Scala sequences. Whether or not something's required, if something's not required, it's a Scala optional. So everything is type safe. So query foos, once it gets out of the executor and gets into our data layer, is already going to have a reified Scala option sequence int at its disposal. and it's going to have to produce an action of a sequence foo. And same for query bars. Query bars is going to get passed to it an option sequence int, and it's going to have to produce another typo, an action sequence foo. I'm sorry, bar. Action sequence bar. So those are our arguments there. Now, how are we going to express that in Sangria? Well, to express that in Sangria, we actually have to make a value to represent any arguments. So what do I mean by that? So here, we actually have to make a value, IDs, which has type GraphQL argument, option sequence of int. And this is essentially a parser that the executor can use in the middle of fulfilling queries. So it just has some kind of meta information about the ID. This is kind of, basically we're taking this schema and we're kind of compiling it into Scala code in a certain sense. And so we say, okay, well, what is this argument? This argument has a name, IDs. This argument gives you, or this argument must be formatted as a GraphQL option, so it might not be there, of a GraphQL list of GraphQL ints. And what are we going to get out of this argument? Once it's been parsed, we're going to get a Scala option sequence int. And that's all we have to do. The library Sangria knows how to take basically a string formatted like this and turn it into a Scala type. It knows how to do that. And again, it's type safe. So if the user gives bad input, it's not going to crash our server. Sangria is simply going to provide an error. But we have to kind of reify these arguments so that we can refer to them later. So we have our GraphQL object that we still have to, our query object that we still have to implement. So if this is a GraphQL object. Remember, we were using the macros earlier, but now this one we have to define by hand. So a GraphQL object whose name is capital query, match the spec. Fields, it's going to have two fields. This GraphQL fields, that's another library function. So it's just their DSL. We need to define the foos field and the bars field. Here we start defining the foos field. Foos field has a name foos. Its type is a GraphQL list of foo. These are both required, so it's a GraphQL list, and we don't have to say it's optional or anything like that. That gives you a GraphQL list of lowercase foos, which were the value we defined earlier. The arguments that get passed. We haven't seen this before because our other fields didn't have arguments, but these fields do have arguments. The arguments that get passed are always a list. Well, this one's a list of one thing, so a list of IDs. And this is why we had to define our argument earlier. We have to refer to it here in the scope, and we have to refer to it in several places. So there's really no way to inline that argument. You have to pull it out. And then the resolve function. So these are very similar. As you see, the only difference is the name and the type they return. We have to define those resolve functions. And we could inline the resolve functions, but it's probably better never mind, it's certainly better to have them in our context. So we already have defined these in our context. We'll simply we'll take the executor, we'll grab the context out of it, and we'll call the query foos method. The executor also has the arguments inside of it. And this is why we have to define the arguments as a value in a larger scope. So we can refer to it we refer to it up here in these dots, but we also have to refer to it here. So we say we're going to grab the context out of the executor. Remember, we've called executor.execute already. We pass it a context. So it has a context. It's going to give us the same context back. We call query foos. We grab the argument out of the executor. Now, let's see. It's a little weird, but I don't know, it's not weird. It's kind of very formulaic once you get used to it. Again, it's almost like we're being a compiler. In principle, this should be kind of generatable, but I haven't seen a library that will generate Scala code. So,
Can you just go one slide? You have here in the argument as a sequence int, then you have list int. Does it matter?
I'm sorry. This list here. This one has to be a list here as it's a field of GraphQL of this case class. This is a case class in the library. And this one has to be a list, but it's going to give us
a sequence?
Well, okay. Well. The list of arguments here and the list that this one argument gives you, those are not the same lists, right? They're on two different levels. So this could have like 5 different arguments. Does it make sense? Yeah. And so that would be the argument list of this method. And so that would be this list here, and this one has to be a list. But this single argument, this one element of that list happens to be a sequence. So it's just the arguments are Scala list, or the list of arguments is a Scala list, but the GraphQL lists kind of map to Scala sequences. That kind of answers your question.
Yes.
Okay. But yeah, we say what arguments this field is going to have, and then later on we can go and pull those arguments out of the executor. Now here is an interesting thing. So of course this line right here is type checked. IDs is an argument of option seq int, and so once we grab this we have an option seq int hypothetically, and so we could pass that to query foo, and it type checks. But there's one thing here that's not checked. It's kind of split up over 2 slides, so it's hard to see, but can anybody see? What's something here that the Scala compiler will not verify, but it's easy to mess up?
The name?
The name, yeah, the name the Scala compiler won't verify, but I think if the name is wrong, it's probably embarrassing, but it's not going to cause the computer to crash. We specify what the arguments are here, and then later on we go and we grab this argument here. But if our program had like maybe 5 different GraphQL argument types, and I say that this field gets 2 of them, like say maybe not IDs but also color, but then here to the executor I pass in, I try to pull out IDs, color, and shape, for instance. Nothing is checking to make sure that I'm only passing in I'm only pulling out from the executor arguments that I've declared. So that's one gotcha. I don't really know of a way to check that, except what we can do and what we always do is we write a test that makes sure that our implemented schema matches our spec schema. And this is very simple, and it runs in a fraction of a second, and it's a tool provided by Sangria. So Sangria can compile this GraphQL spec into kind of a native data format. It can't compile it into Scala code, but it can compile it into a native data format, and it can compare it against the schema that you've implemented, and you can check to see that they're the same. And so we do that. But it's not a Scala compiler thing. We have to write a unit test to do that. That's all I'm saying. So that's implementing your schema, and that is the end of my talk. And now we're going to take a look at an actual, slightly more complicated server that I put on GitHub. So let's take a look at that.
So just one question. So the body of the definition, you have it in a different class or in the tree itself?
It's up to you.
Okay.
Yeah, the way we do it, we put it in a different class. but it's up to you. Up to you.
So how to define which class of, how would the Sangria code know the class that you define that inherit from that?
So it will use whatever, when you go to execute your query, it will use whatever DAO you passed in. So here, when you call executor.execute, you pass it a value that has a type that you specified in your schema.
Okay.
Yeah. So we specify our context here. We create one. And what we do is when the request comes in, we use the auth token and some other information from the request to actually create a new schema a new context every time. In principle, you don't have to. Your schema is a global, and your context could also be a single global if you want to, but the way we do it, we happen to create one with every request. And you pass it in, and it will use the one that you pass in. Yeah. Good question. The structured part is kind of over, so the rest we can kind of play by ear. We can just kind of like talk about the server here.
Guys, I don't know how big your API is. Is that context anyway like partitionable, or you just have multiple threads and then combine into one and give the type?
We could do,
I can imagine like for bigger APIs it can get like massive.
Yeah, that is one thing that we run into, and so one thing we do about that is there's no reason that there has to be a one-to-one mapping between the methods of the context and the resolvers in your schema. So you could have several different resolvers call the same context method, for instance. So let's take a look at the slideshow to see exactly what I'm talking about here. When we look at the slideshow.
But in real life, since you're already in production with this, how big your graph query right now? Like how many schema do you have? How big is the schema? Let's start with
this. So our schema, so basically, before I forget what we're saying, like we have one method in our DAO that gets the bars out of a foo. Mm-hmm. And we have another method that gets the foos out of the bars. And then we have a top level method that just gets bars and just gets foos. And the two methods that get bars, those could be the same. You know, they don't have to be separate methods. They could be the same. And then the resolver calls it with appropriate arguments.
So my point is, let's say you have in a real world, like say 200 model objects, right?
Yeah.
And let's say just crowd of it, it's just almost 1,000, right?
Yeah.
So obviously, for not every model you would necessarily need 4. You can also have this context having all those methods.
Right, like 200 methods.
So you definitely want to partition.
Yeah.
From what I saw in the schema level, it says like, okay, give me the type of your context, right? So it assumes like even if you partition, at some point you have to combine everything together into one tree.
Yeah, I mean you could totally do that. You could make a class hierarchy for your context like you're talking about, and then partition it. So like maybe certain like bar needs a particular context, and then foo needs a particular context, and you can keep them separate that way, and then implement them. Make one that implements everything to tie your schema together, right? So you could use like mix-ins or something like that. Yeah. So you could definitely organize it like that. I mean, you can organize it better than this token.
I'm trying to understand like how you guys do it in a real world system, like what best practices you use.
So let's take a look at in a real world system. So we have our GraphQL schema. We can actually take a look at it right here. So here's our schema, and it's kind of long. Let's see. Let's open this in Sublime. Actually has some nice syntax highlighting for GraphQL. Okay. So here's our schema, and we don't have a lot of types. We have an advertiser commission. We have some scalar types. Those are essentially enums. There's also a GraphQL enum, but we didn't want to use specifically GraphQL enums. We wanted to think of these as like one of these 5 strings. I don't know. So we could use enums or scalars. We chose to do scalars, and we use kind of a Scala refinement type pattern to say it's a string. It's one of these 5 strings. We have advertiser commission, which we don't have a lot of types, but those types have a crap ton of fields. Advertiser commissions. This is a common pattern in GraphQL API is you'll have a wrapper that has the list of commissions, but also some page information, count, limit, cursor, or max commission ID, things for. So our entry point will return an advertiser commissions, which has a list of advertiser commission and also some paging information. Let's see, so we have this type here. We have advertiser custom pixel, which has a bunch of optional parameters. Notice those don't have exclamation points, they're all optional. We have a commission. We have a commissions. These we're deprecating because we want people to use specifically advertiser commission or publisher commission. Custom pixel, some more scalars. We have an item, which is nested. Every commission has a list of items. Publisher commission. So we have, what is this? This is about 1,000 lines. Much of it is doc strings, which you actually will see when you look at our server. You'll see these doc strings. The Scala implementing this, so 1,000-line GraphQL schema, give or take, well, maybe cut it in half, maybe. So maybe like 500 important lines or something like that. The Scala code we use for this to implement this server is about 5,000 lines. And that's counting unit tests. So the major win there is the macros. So we have some case classes that represent the data layer. And we use a macro. Of course, the data layer doesn't match the schema. That's the point of GraphQL. So we only have to go in and change about maybe like maybe like a dozen things. We have to go in and change. But much of it can simply be generated by the macros. So that is pretty cool. We're very happy with the small amount of code that we have for our API. And as we expand it, of course, it will get more. What's interesting is we split commissions into advertiser commissions and publisher commissions. We split it into different types, but we didn't have to repeat the case classes at all. We could make mix-in traits for those case classes and simply use the same underlying implementation, and then and everything, that usually when you do something like that, you worry about how that's going to interact with the macros, if it's going to play nice with the macros, right? But it works fine. It works great. So we didn't have to repeat anything there. So we're very happy with it. But let's take a look at the one thing that annoys me is the docs. You saw everyone else's docs look very nice and formatted and pretty printed, and our docs are nasty, and I don't know why. It's generating these docs from the API. So we didn't tell it to write this. This is the method that we have, and it gives you a list of commissions. The only thing that we wrote here is this string right here. Or if we look at max commission, that has a string. No, not that. Max commission ID, unique ID of the final commission returned by the call. So we wrote this, but then this, but the rest of this documentation is all generated for us. That's a great win. We wrote this, but then here, yeah. The other ones we looked at, though, it was nice. The methods were nicely formatted, and these ones are just trash. I don't know. But it's probably just a setting on GraphQL, so we have to just figure out how to do that. And then I don't have a valid key. Actually, I do, but we can't use that here. So we can't actually see this data. We can see the demo one. So let's look at that. So here I made a slightly more interesting API than the one that we saw in the presentation. The presentation has to be very simple because we have to talk about it. But this one, we have shoppers, we have items, transactions, and a transaction item. And the idea here is every transaction is going to have a list of items, but we want our database to be normalized. So we don't want to store an array in a database column. So we have another table for every item in a transaction. So this is typical normalized database. And then we denormalize it in the schema. We have a shopper. Of course, a shopper has its database columns, but it also has, we have transactions. For every shopper, we can look at transactions, and we can restrict by dates, or we can restrict by, I only want transactions that have certain items, something like that. Here we have items. Of course, they have their database columns, but we can also say, well, what transactions were an item involved in? And we can restrict those as we want. Here's transaction. Transaction has a shopper and a list of items. So we have all these relations represented kind of as nesting. It's really like an ORM in a certain sense. And we have our entry point. We can grab shoppers by their IDs. We can grab items. But the main thing here is transactions, and we can filter them by various parameters. So how do we implement this? So to implement this, now.
So where did you store that? This one is like that. Yeah. No, not this one.
Yeah.
This one. So what? This is like query language.
Schema definition language.
Okay.
Yeah. Yeah. We store this. So the one you were looking at just now. If we go back here. This one is actually generated for us from the Scala schema. So this is not the way we wrote the schema. We did write all the doc strings, but this is the schema itself is kind of pre-printed for us and generated for us. But we do have a copy that we wrote by hand, which we consider the spec. And we work with our product owner, and we work with our stakeholders and other companies to kind of like work out this SDL as a spec for our project. And then we have a unit, we keep it in, we basically just keep it in another Git repository. But in our unit tests, we import it and we compare it to the implementation and verify that they're the same. Yeah. So that's where we keep it in another Git repository. It doesn't have to be in here. Ideally, we would want to generate our Scala code from this. And it seems like in principle it should work, but I'm sure there's some gotchas. But it's something I've been thinking about a lot lately. Because really the only place where we make choices is where we implement the DAO. When we took the SDL, the schema definition language, and then wrote out the schema in Sangria library, there were not a lot of choices for us. So I think in principle that means we should be able to automate it and generate that Scala code. But here's our server. So let's just run it, and then we'll look at the different things. So here again, I've aliased some of the things that I'm importing from the Sangria library to make it more obvious. We have Sangria error with resolver, executor, query parser, and syntax error. Our server have a method for formatting error messages in a way that's appropriate for GraphQL. If the executor creates an error message, it will be formatted already. But if my data layer creates an error message, I need to format it. So this formats it into appropriate JSON. It should have a data, and it should have an errors array. And it's just the GraphQL spec. Handle post. Let's look at that in a minute. GraphIQL. So our server will actually serve GraphIQL, and I just keep the HTML in the resources directory in the class path. Our server is going to run on port 80. And when we make a GET request, we're going to serve GraphIQL. When we make a post request, we're going to serve, we're going to call handle post. When we do anything else, we give an appropriate HTTP response. So all the main stuff here is in handle post. In handle post, we grab the query out of the, we parse the query out of the request. So this is just some JSON parsing to parse the query. Parse query, unable to parse. Here we have the parsed query. We get, let's look it back. All this is happening in a for block over ithers. So I have either response to response. The left would be an error response. The right will be a happy path response. So here, this catch method will, catch anything that throws and turn it into an either, a left either. We grab the query out of the request. We try to parse the query using Sangria's query parser. Now, the query parser doesn't throw, but it gives you a try, right? So it gives you a reified error. So one of the errors it can give you is a Sangria syntax error. It could also give you kind of any throwable, and I don't know why, but it can, so we'll have a 500 response in that case. Just cover it, make sure we cover everything. This one's probably paranoia on my part. Really, this is the main thing that the query parser might do, is it will show a syntax error. In which case we have a bad request, 401. Now executor.execute. We give it our query, we give it our schema, we create a context if we want to. Here we're using the auth token to create a context. This auth token doesn't do anything, but just as a way to show how you could do it, you get an auth token out of the request and you use it to create a context. Executor.execute gives you a future, so I'm going to wait 1 minute and I'm going to give back, these are the different things that might happen. We might have an error with resolver. Now the resolver there doesn't mean a resolve callback or in your schema. It just means an error that we know how to format. It just means an error with this resolve error that will format it nicely. So we give back a...
So it's then a future, then you wait for 1 minute? That's how it is?
Well, yeah, my HTTP library is very simple, right? So it's a different, it will create a different thread for every request. It's just standard embedded Jetty.
Yeah.
This one will create a different thread for every request. So I do block on this future, but it's fine because I'm in another thread anyway. The futures are just used by the executor.execute and by our data layer. So our data layer is probably asynchronous, right? So every method we write in the data layer, we probably want to make use of Scala futures or something similar to handle asynchronicity. So while executor.execute goes on and everything in our database starts lighting up, or in our data layer starts lighting up, they're all going to be futures. But out here, I wait a minute for all of those to resolve, and because we are serving an HTTP request, we can't wait for much longer than a minute, right?
Yeah, I mean it's the long even.
Yeah. Here we have, so we might have a timeout exception from the future. We might have an auth error for whatever reason. Maybe they're unauthorized. We might have a error with resolver. These are usually going to be where the query is syntactically correct but doesn't reflect the schema. It's a pretty bad name for it. I don't like the name. It should be a little bit better. But these are basically, they're bad requests because they have a syntactically correct response. The parser didn't catch it, but when we check it against the schema, the query's no good. And Sangria will tell us exactly why, and we'll have a line number and a character, line and row number. Auth error, timeout exception, and who knows what else. If I call some database functions, they might throw, so I want to catch those. And if everything goes right, I want a 200 response, and that's my post handler. So now the interesting parts are the context and the schema. When I say the context, let's drill into that. So what do we have here? We have here in our package object, I basically define a couple types that I'm going to use for my HTTP. It's a very rudimentary thing. They're just type aliases, nothing very special. But here we go. Here we have the auth error that we caught earlier. Just make something to catch earlier. Now we have our we start looking at our database objects. I'm putting them in the package object because they need to be used by both the schema and the data layer. So we have a shopper here. We have item, transaction item, and these four things match our table exactly. So each of these matches a table, or matches a row of a table. The context here, this is pretty big. And so again, for a small API, What I was going for here is just to make a separate method for every single time we needed to write a callback in the schema. We don't have to do that, but that's kind of the approach I took here. In our production, we actually take we take the approach of everything in the schema kind of more or less calls the same method, but with different arguments. But here I wanted a separate one for every callback. So when we go to look at our schema, each of these will be called exactly once in the schema. And just a couple things for converting futures into eithers. I did my pipeline, my request pipeline using eithers. So I have a couple things for convert a future into an either, convert a try into an either, convert an option into an either, so on and so forth. And then this little converge right here. If I have an either with the left and right being the same, then I can grab the payload out of there safely. And that's what I do in here. At this point, we have an either response. And so I say, well, those are the same. I just want whichever one and serve that up. Okay, so these are basically our case classes or types. Then we go to look at our, the data layer in this one is very boring. This is just an in-memory, I call it falso-DB. It's just a bunch of fake data, right? So here is where you would write your interface to the database. Here I implement the DAO. So I have a method here called context, which gives me a context that implements all the methods. And it implements them by basically looking up from these sequences. So it's just a fake database, right? So this is our.
Can you show how you create an instance of an auction?
A
Sangria auction.
Yeah. So sorry. Yeah.
How you instantiate it?
Right. I wanted to talk about that more. So right, a Sangria action. So we drill into that, and here we're looking now at the Sangria library. So we have all these things that subclass action. So we have deferred future values, deferred leaf actions, all kinds of things. I think a leaf action just wraps a value without any extra effects. But then a deferred future value, that one can wait until you calculate something else, and then it can be triggered later. So there's this whole class hierarchy of different types of actions that provide different kinds of side effects, if you will. So
if I already have a helper method, let's say give me all the users or give me orders for this user, right? The more realistic one, let's say somebody already wrote service or database and it's a client and it returns me a future, let's say future of either. Let's say future of something. Future of transactions. To not worry about the details. How would I convert it to some reaction?
So futures are also there's an implicit conversion from. So first of all, if you have any type T, there's an implicit conversion from T to an action of T. So it does. So
you can lift it.
Right. Yeah, exactly. Yeah, you can lift it. Yeah. Then futures also there's an implicit conversion to lift a future into action as well.
Oh, nice. So as long as I have it in my context, I can even return a future.
Right. Exactly. Yeah. So so I don't always know how much Scala to talk about at these talks, but yeah, I mean there's a bunch of implicit bunch of implicit conversions, and really it's if it means anything to you, this action type is not a monad, but it's an applicative functor.
Okay.
So the difference between monad, of course, you have flat map, but with applicative functor, you have a method called sequence, which takes a list of actions and then turns it into an action of a list, right? And you think, okay, if you have flat map, you can implement that sequence method, right? But we don't have flat map for actions, and the reason is because if you implement this sequence function in terms of flat map, it has very kind of shitty performance.
Yeah, flat map is very bad.
Well, but just the idea also that it has to happen, things happen sequentially, right? And with applicative functor, you could convert a list of actions into an action of a list, and all of those can happen concurrently. So really, that's the idea. That's kind of the idea behind this. Is it's kind of a very large kind of it's kind of an effects functor. If you do like Scala Z or cats or something like that, they always have like an effect type that does all kinds of I/O for you, and it does futures and parallel concurrency for you. And Sangria has its own kind of it has its own effects functor called action. But there are a lot of implicits for these other ones. So for instance, future is implicitly an action, right? And then I think cats and Scala Z effects are also implicitly actions. So you could use, if you're using some other like high-powered I/O effect library, it fits nicely with Sangria. But they provide you one if you're not. We're not using really the full power of this either. So we take a very simple approach, and we just basically put everything inside the futures in production. Basically everything is a future, and we just let the Scala standard library handle it instead of the Sangria library. But then it converts, it lifts into it easily. So yeah, where is it? It's I want to find, yeah, here it is. So this sequence is unfortunately named because it doesn't happen sequentially. They can happen in parallel, but it takes a sequence of actions. You can take a sequence of actions and turn them into this sequence leaf action, which subtypes action of sequence. So you could basically like, you have a bunch of actions, you could factor action out and have it on outside and have a list inside. And you use that if you want to run a bunch of things in parallel. That much is kind of a lot of fun, but we don't kind of go into it here because we just have this fake database, and we don't go into it, but we do go into the schema def here. So the schema definition, when we go to define the schema, again, we make types for our arguments. These arguments are just the arguments that are in the spec. We can actually also share them between different things. So if we pull up the spec again, transactions. There are several different transactions fields, but they can share the same argument. So this since date, since it's the same name and the same type, it can be shared with all of these. If they're different name, different type, we have to make different schema values, different values here for them. But as long as they're the same name and the same type, we can share them. They don't rely on any extra context. So we declare our arguments. We define the shopper type, and again, we use the macros to define the shopper, but we have to add extra fields. We define the item. Again, the macro is doing most of the work here, but we add an extra field. So when we think about how much work the macro is doing, here's what it takes to define one field, right? And if item has like a dozen fields, right, we'd have to write all of these out. But but most of them are already in the case class, and when that is the situation, it knows what to do. It does the obvious thing. The executor passes you an item, so you pull that out of the executor, and then you drill into the field. And that's the kind of boilerplate that they're all doing, but the macro is doing, but it's just doing a lot of boilerplate for you. But then when you have a computed field or a modified field, then of course you have to specify that. So here in transaction, we replace shopper ID with actual shopper. And then we write our query. And query is not based on a case class, so we write it out by hand. And we specify the fields it has. Its fields are shopper, items, transactions. And we say what the arguments are. And that's our schema, 140 lines, so not so bad. And a lot of them are these aliases. So let's run our server. Oh, and just one more thing, if you're interested, this is the embedded Jetty. It should be pretty standard. It's nothing special. So it's a Java servlet something, something, something. So let's run our main. I cross my fingers. I haven't run this in a couple of weeks. Okay, so this is just a standard. What port is it on? 8080. Okay, thank you. Let's take a look. Here's our GraphQL. This is my work. Let's separate my work out of there. Let's get the shoppers, and we want, of the shoppers, we want their ID. Let's get their name. Let's get their transactions. And of their transactions, maybe we only want transactions that have to do with particular items. So let's get transactions that have to do with item ID 1. And of those transactions, let's get the date, and let's get the other shoppers who also bought this. So I want everyone who bought, I think it should be an int instead of a string, everyone who bought this same item that, or let's not say item 1. Let's just say all the items. No, let's do this. See what we get. So we get shoppers. We have shopper 0, Lisa P. Hacker, and on this date she bought item ID. It doesn't tell us what I want to see what they bought. Let's see, transaction, items. Yeah, I wrote the wrong query. This is what I really want. I want to see the transactions. Let's actually drill in here and say shopper IDs. Alyssa is shopper ID 1. So okay, here's what I want. I want Alyssa's info, but I want all of her transactions. I want the things that she bought, and I want the other people who also bought that. That's what I want. So like something complicated that you'd write SQL for and you'd write a join for. I want this person's transactions. I'm going to see the items, and I want the people who bought the same items. So Alyssa bought Learn You a Haskell for a Great Good, and so did C Defect. So Alyssa bought it, of course. C Defect bought it twice. I guess it was really good. They only have so many people in here, so they're going to repeat a lot, right? But this is basically, you can get this very nested, deep information by making, with kind of simple queries, and it's kind of a la carte. Again, the main idea here is that GraphQL is REST a la carte. So thank you very much for your attention. I hope it was very illuminating, and I hope, if you, let's see, I know that we're all in LA, but I'm in the Santa Barbara Tech Slack channel where you can actually ping me, and if you have questions about GraphQL, and if they're quick, if I have time, I can help you out or anything. So again, thank you for your attention. Thank you.
This is great. Thank you very much.
So the repository. Where's the repository?
Yeah, I'll post the link to the Slack channel.
Okay.
And to the repository on the.
You said you were in West, right? We host a meetup there as well.
Oh, is there a Slack channel for this meetup?
There isn't yet.
Okay.
So
I'll join that one.
I was gonna ask, is that what is like? Is that how you would all prefer to communicate, or Discord, or?
Chat's fine.
Okay, Slack then. Okay.
So here is the GitHub repo. Here's the Git repo on GitHub, and there are a couple branches because I gave several different versions of this talk. The master branch is a little bit simplified because it was for a meetup. It was for a Java meetup, and we're kind of introducing Scala at the same time, so we didn't get to go as deep. So this one here, use the branch Scala meetup, and we have the presentation in here. Well, the source code for it. and we have the source code for the server as well. And you can it's a Maven project, so you can use Maven to download all the dependencies. All the dependencies are open source, so you could just download them and you can run this